expand our Zoom license and see if we can just use it. That seems to be a lot more intuitive for most people. Anyway, he sent me a whole ton of follow-up information, a really nice info packet, all kinds of links and stuff like that. So I'll put that together and get that out to you. I'm also still working on closed captioning last Thursday's forum. So I'm complete noob to learning how to close caption things. So the MS Teams software actually detects words. It recognizes words and closed captions. But at first I thought, oh, that's great. It's just gonna fix that really awful audio we had with Bill Petrie. But then I went and I started reading the words that it found, and they're not correct. Like whenever he said vaccinate, it said vacillate, or it said, something totally different. So I'm going to work on that and hopefully get that to you over the weekend. Let's see. Remind me how far we got last time. What did we do last time? Sweet. So we started talking, I showed you the basic ring ideas, and I think that I glared at those of you who have not installed the CAD software. I want you to really try to get the CAD software installed this weekend if you haven't done so already. And if nothing else, just get to the point that you can do a simple 2D sketch. How many of you are using Fusion? Some of you are using Fusion? Okay, maybe what I'll do is I'll make a little helper vid on Fusion. Fusion is actually very, very similar to Inventor in a lot of ways. Just for some reason, there are some things like embossing and extruding. For whatever reason in Fusion, they call it press and pull. I don't know. Anyway, I have a Mac and I use Fusion on that. And then on the Windows boxes, everything else I use Inventor. So I use them pretty interchangeably. So you won't be at a disadvantage with Fusion. If you're having difficulty installing software, if all else fails, one tried and true method is just to install a 30-day demo if you're having issues with licensing or whatever. But I'm hoping that most of you will be able to get your UVA license up and running, since it is licensed for, I think we're licensed for about all the Autodesk software. Okay, so what I thought I would talk to you about today is the 3D printing process. So did I talk to you at all about Cura or overhangs and fast access and slow access? Okay, this is good. I'm seeing a lot of shaking heads, so that's good. So what I've done is I have, what we'll be doing is we'll start 3D printing, and as soon as you have a design that you think is worth trying out, we have 3D printers here, and we also have some fancier ones across the way in mechanical and aerospace. There's a facility over there called the Rapid Prototyping Lab, and my buddy there, Dwight, runs that, and he can print us out really, really high quality stuff. I think I may have passed, I don't know if I passed, did I pass this around last time? Okay, I'm gonna pass around this. Let me just explain what it is, first of all. This is a really, really cool three-dimensional object. It's a gyroid. And if you look at it, it's a little bit of an IQ test to figure out what the heck that is. It's a plastic object that has, you could think of it as like a bunch of beams that go this way and then a bunch of beams that go this way and then that way and that way, like a waffle, sort of an alternating waffle kind of design. But it's three-dimensionally connected. What makes this design so really special is this is not something that you could make subtractively. Okay, subtractive manufacturing means, like, suppose you get a block of material and you just chisel away at it. If you try to make this thing that way, good luck. It's a very complex three-dimensional shape with a whole bunch of voids and all that. So this is a really nice example of something that you pretty much can only make by 3D printing. So I'm gonna pass this around the room, and if those of you who are remote are wondering what the heck that is, you'll see in a second. I'll show you a model. So let me just toss this around. We've got, by the way, we've got sanitizing fluids and all that kind of stuff over there if you need to wipe your hands or whatever afterwards. Okay, so while that's going around the room, what I did was I CAD'd up a ring here. Let me get Keith 2 fired up here. Keith 2 is going to share his screen. He's going to share his CAD screen. And while you were resting, while you were sleeping, Keith 2 made some goofy ring that has some wraparound text, right? Like that. Okay, fairly simple. And now what I'm going to do is I'm going to talk about the process of 3D printing this. Okay, no, we're not going to be able to 3D print in gold, but too bad. We can 3D print in plastic. So what I did with this is I exported this in a format that we can open it up in some what's called slicing software. So we take a CAD model and then we have to slice it. The way the 3D printing process works, you put down one layer at a time, and we need to tell the printer what each of those layers is. So we need some additional software, not Inventor or Fusion. We need some additional software that takes our CAD model and does sort of the sushi slice on it, you know, and slices it really nice and thin. And then we send those layers to the printer, and the printer prints them out. Cool. So the slicing software that we're using, there's a bunch of different slicing softwares out there. The one that we use in here is called Cura, C-U-R-A, and you can install that if you like. I'll show you the way it looks here in just a second, and I have it working on my Mac. It's free. Cura is a really nice, fairly standard thing that we use with the Ultimaker printers. We have 4 Ultimaker printers here in the room. Actually, 2 are in my house, where I spent time over the summer playing with them. And we got 2 more in here. So I'm gonna have some printers set up here. And then, like I said, we'll also have printers across the way that you can use cost-free. All right, so I'm gonna take this design, and what I did was I saved it in a format that we can open it up in Cura, and that format is called STL, stereolithography. So what you do to save this, right now notice that this is just a part file, it's .ipt, and what I'm gonna do is I'm gonna do export, CAD format, click that, and then select, there's a long drop-out menu here, and I just select .stl, and then I just called it wraparound text. Okay, so that's how I saved it, and then I emailed it to myself. So now I'm going to go over to my other computer. Let me stop this share. I'm going to go over to my Mac here, and let's see. I emailed it to myself, so let's see if I can find it. Just a sec. Give me 1 minute here. There it is. Wraparound text.stl. Okay, so now what I'm going to do is I'm going to share my screen. I'm going to share on my Mac. I'm going to share my Cura screen. This is what the Cura software looks like. Right now, it just looks like an empty print plate, like a 3D printing print plate. Okay. I think everybody here can see that, and everybody online can see it as well. And so we need to, now what we need to do is just open the file. Let me space this out just a little bit. There we go. I'm going to open the model, and the model is wraparound text.stl, and there it is. Very common problem. Where the heck is my ring? Oh, if you look really super closely, you can see that I forgot to embed the scale, and it's this little tiny thing. This is a very common mistake. I'm glad I made this mistake. I could have embedded the units into the file. I did not do so. And as a result, it just defaulted to, like, I think it interpreted inches as millimeters or something like that. I didn't tell it which units to use. All is not lost. What you can do is go to this, this option over here, and it allows you to scale as much as you like. So now I'm gonna just scale it up really big. I'll scale it like 1,000%, and that probably takes care of it. All right, so now we have on this print plate, I'm just gonna drag it. Let me zoom in a little bit so you can get an idea of what we're looking at here. Okay, so now we have the CAD model. Notice if we look at it from underneath, we see some red. Does anybody know what that means? That is unsupported print. So just imagine how the 3D printing process works. So first of all, let me go ahead and slice this file just to give you an idea of how the 3D printing, how the software works. And so I'm just going to click. This is really straightforward. I'm just going to go slice. I have a little swig of coffee. I wish I had some. And go like that. And then I'm going to actually show you, now that I've sliced it, I can actually do a sort of a print simulation. I'm going to go to preview here, and I can actually step through the layers like so. And I can even click play here, and you get a lovely animation of how the 3D printing process works. Pretty handy, huh? So let's go back a couple layers here. And let's start off with the raft. So first of all, the very first thing that we put down is this raft. What's the reason for the raft? Those of you who have 3D printed before, you know what happens if you don't make a raft. If you don't adhere the object you're going to print to the print plate, then you got yourself a problem. The print can actually move around over time. And that's not good. And then you'll wind up with that, probably those of you who've done some 3D printing, you must have done some mistakes as well. You get a sort of a convoluted, spider web of plastic that's not attractive. Notice that the way the printing process works, this is a lot like putting mustard on a hot dog or icing on a cake. You just squeeze out some molten material and it lays down like that. And so that's the way this thing works, is it just kind of goes like that and squirts it out. So what do you suppose defines the resolution of the print? What limits the resolution of the print? There's actually two different resolutions that we talk about in 3D printing. There is the lateral resolution, which is what you see here. It's all in one plane. What do you suppose limits that resolution? So those of you who have experience icing a cake or putting mustard on a hot dog or something, what limits the resolution? How finely, like if you wanted to write your name with icing or something, what limits that? What's that? The size of the tip. Okay, so if you look in very, very closely here, you can actually see that there's a little tip here. And so like if you've ever iced a cake, or like if you use a plastic bag and you snip off a hole, and then the icing comes out that little hole, roughly speaking, the resolution, the lateral resolution you have is the size of that hole. The hole is what we call a nozzle. And the nozzle in this case is a very extra fine nozzle, 0.06 millimeters. That doesn't, by the way, the 0.06 millimeters does not necessarily mean that you have that's your lateral resolution. That just means that's the exit nozzle. And then the material tends to kind of splay out from there. So if you want to get the very best resolution, you have to actually have the nozzle very, very close to the material. To the plate. And if it's very close to the plate, then you can in fact get that kind of resolution. If you screw up, like if your print plate is a little bit at an angle or something like that, then the resolution gets screwed up and you don't get such a nice result. Cool. What else do you suppose limits the resolution, the writing resolution in the lateral direction, in the XY direction, say? Again, think about writing your name in mustard on a hot dog or a hamburger or something, or icing a cake. What limits the resolution? It's how what? Yeah, so if the material doesn't flow well, then that's a big problem. You know, they have that issue with ketchup, right? Like you can't write with ketchup because it's kind of globby, whereas the mustard tends to flow out really nicely. And a lot of icings, maybe sometimes you warm it a little bit. I think if you put take your icing bag and put a little bit of warm water, then it's super runny and you can get really high resolution. In this case, the material is heated up quite far, 200 degrees or something like that, and it actually flows really easily. There's another issue that you would be experienced with if you tried to write your name or something in mustard or icing, is how steady is your hand, right? Now in that case, we're using motors here. We're not using the human hand, fortunately, to write these features out. So we're lucky. The motors, the XY motors on a 3D printer are extremely fine control. And they don't have tremors like our hands. Our hands, they don't jiggle around or get nervous or anything like that. So we can actually, that turns out not to be a limiting issue. That turns out not to be a really big issue. Notice also, please notice that, and let me just go forward into a more interesting part of the ring. Let's go out to like here-ish. Notice that the nozzle actually prints quite quickly in the XY plane. You notice that it can actually cover a pretty large distance in the XY plane. Do you notice, oh, by the way, if you look at this
film. This one's fully online. I should find this one's online.
What's that? Is that okay? Notice you may see that there's a really weird fill pattern happening here. I actually selected gyroid fill. So that blue object that you passed around, I'm using that fill pattern for this ring. That's why it looks kind of like zigzaggy sort of thing. Look how quickly it writes along the XY plane. Okay, this is what we call the fast axis, or maybe we should call it fast axes or fast print plane. In the XY plane, the printer can move very, very quickly and it can spit out plastic really, really quickly. Contrast that with the vertical direction. That's much, much slower. Why is the vertical direction so slow? Because it has to complete each layer. And it can't go on to the next layer until it's done the one immediately below it, right? And look at this. You might be impressed by how quickly it's printing in here, but we're only on layer 91. If we had to go and print this entire thing, this one gets divided up into 300 some odd, 500 layers. So that's not good. The other issue that we have here, if you simply rotate this thing and look underneath here, so let me stop the print simulation and just move it up like that. So you can see, I made some reference to some red there. What's the red here? That is unsupported material. So that may be a bridge too far, right? If you start printing, we probably can print all of this fairly well, but when we get up to this point, now the print doesn't have any support underneath it. So typically, whenever we're printing something like this that actually has a sort of a overhang, then we typically have to come in here with our print options and we have to say, please generate support. And if we generate support, let me just point out one thing here. Let me find this. There's the support. First of all, notice how long it says it takes to print this ring. It says 1 hour and 45 minutes, and that's at super duper high resolution. So that's actually not too bad. I think that's okay. But if we start generating support, and we got to reslice it, then we're going to have a problem of time. Because now, in addition to writing the actual ring itself, we have to actually generate the support. And the support material, let me go back into the simulation here. You're going to quickly get the idea. See all that support material it had to generate? And it had to generate that support material there. See all that extra crap it has to write just to support the top of the ring, right? So it adds extra time. And this is still a relatively fast printing design. So it's not too terrible, but you can kind of get the idea that it can add a lot of extra time, especially if you have a really three-dimensional object. Like suppose you're going to print like a coffee cup. I had a student who made a coffee cup and something like that. That might really take a long time. Okay, so some vocab you've got. You've already got slow axes and fast axes. The slow axis is the vertical axis, right? And also take a look at this and what limits the resolution along the vertical axis, along this direction upwards? The layer height, right? How many layers you slice it into. In this case, I sliced the holy whatever out of this thing, and I've got 500 layers, so this is about as slow as print as you're gonna get. I could have gone with a lower resolution, but the problem with that is at some point, you start to mess up any kind of text that you have along this side. So let's take a look here. Let's stop this simulation. And let's just take a look at the actual print design and see if it even makes sense to print it in this conformation, in this configuration. So what I did was I made wraparound text, and then I just put the ring like this. So let me offer you a couple of options here. I can print the ring like this, or I can print it like, oops, like that. You tell me which you think is the better. Would you rather print something like this or in the other way vertically? This particular ring, which way would you rather print it? By the way, let's slice this now and let's just see from a standpoint of time. Okay, just a pure standpoint of time. All right, the amount of time that it takes to print something does depend on the orientation in which you print it. So let's go ahead and slice this again. and see. 1 hour, 30 some odd minutes, 38 minutes, so quite a bit less time. If we included support in the other method, then I think we were up around the 2.25 hours. This one's like 1.5. That makes a really big difference, right? So seems like a no-brainer. It's the same damn ring. Why don't I print it out this way? It'll come out faster. Why would I not want to print it out this way? Any suggestions? Any thoughts? Yeah. Yeah, so the issue, if you print it this way, he's saying maybe it'll mess up the text. I think you're getting at the sort of the resolution issue. And as we look through, remember what limits the resolution along this direction? What limits the resolution is the layer height here. Now we don't have nearly as many layers. We have 140, 145, 144 layers this way. So the resolution is not super duper. You can tackle that issue simply by using bolder text. So one of the things I always tell people is please don't make, if you're gonna make like the One Ring or something, like make it bold. Don't make super small curly cues and stuff that just won't render well in a 3D printing environment in the first place. But yeah, so now you're limited, your resolution in this case now, your text resolution is now limited by the layer height. And so that may not be optimal. On the other hand, maybe this is better. Now we've got one thing, consider this much, at least your text is gonna look consistent all the way around the ring. So maybe your text is at a lower resolution, but now all of it is at the same resolution. Consider the issue that we had before. Whenever I had this ring popped up vertically, let me see if I can get it back up into this sort of conformation, like so. We had this issue. I leave it as, it's kind of a matter of opinion whether this matters or not. The very highest resolution is going to be right on the tip top up here. The text that is on the XY plane is going to be super duper high resolution. It's only limited by the nozzle, that's it. And the nozzle is super, super, super fine. So it's not layer limited. Okay, so you have very high resolution. What happens to the resolution as you go down here? Over here, the resolution is limited by layer height. So if you look at this text, as you look around the ring, it's actually going to be printed in different resolution in different places. And maybe that may not work for you. It may not look good. It may work fine, it may not work fine. So hopefully this is starting to give you some ideas as to how 3D printing considerations cause you to actually change the design of your ring, right? If you have something that you want to print in super duper high resolution, you want to make a realistic bust of your instructor and put that on the top of your ring, right? And your beloved ENGR instructor, and you want to make that face super realistic with a big nose and everything and the glasses, then you better do high resolution and just have it printing in the lateral direction, right? If you're layer limited in that, then it's not going to look good, right? If you're going to put TJ up there, if you're going to put a rotunda or something like that, then you probably want to print it with the really, really fine features facing upwards. Another issue that you could run into, and I'm not sure if I ran into it here, let's just see. Here's a funny issue that can happen. See that I've got some of the text that actually goes on the underside of the ring. That's going to get buried inside whenever we do the support. Let me go ahead and slice this model. That is actually going to get buried inside the support. First of all, it takes longer. Let's go back to our simulation here. And let me move this up so everybody can see it. Notice that the text is kind of buried inside here. So if we go back to that particular layer, the text is buried like right inside there. It's not the end of the world. You can still get pretty good downward facing text. But as Kyle can probably attest, I don't know if he had this issue, then you wind up having to dig support material out, and that's a pain. What can really save you and make you a happy person is for example, that gyroid, that 3D printed gyroid thingy that I had there, we have printers over here that have dissolvable support. So it prints with dual filament or even 3 or 4 different filaments at the same time. So it prints the plastic part and then it prints the support in a different material. And that different material can then be dissolved after the print is finished. So what we do is we take, that's how I got that really super duper high resolution print on that gyroid cube. We printed it with dissolvable support. So what you do is you take the model after it's printed, the whole thing, and you toss it in some NaOH water, just lye, right? And that dissolves away the dissolvable support. And then you're left with just the plastic, and it's really beautiful. Okay, so these are just some standard 3D printing design considerations. Now let's talk about some things that, some tips and tricks. So here's some things that only 3D printing can do. And those of you, especially those of you who have experience with 3D printing, you already know some of this stuff. So feel free to jump in with some examples if you can think of them. What I'm going to do is I'm just going to clear this model here, clear the build plate. And I'm going to, some years ago, I was interested in, was working with Professor Lisa Closey-Peterson, and we thought it would be fun to crush some, make some like cylinders and crush them. And so this is a cylinder that I made. Actually, I didn't make this. I was so totally cheap. I cheated. I found this model online and I just swiped it because I liked it. So let me go ahead and prop this column up the way you would normally see it, like so. Isn't that lovely? Pretty nice column. Let's look at it in some detail here. Oh man. I'll move the model up like that. Okay, so you can see this model is got some pretty cool detail. You can see why I didn't want to CAD it myself. Somebody actually went to the time to make these lovely curly cues and all that. But the part that we're really interested in here is the column. I'm just going to go ahead and slice this up so that we can have a look at it. Okay. Sorry, that zoom thingy always gets in the way. Actually, I can put that away, can I? Hide video panel. Hide floating media. There we go. Now you have to remind me where those went. Okay, so now it's slicing, and this is a pretty big model. You can see the actual dimensions of the thing. It goes up by about 5 centimeters. So it takes about 2 hours and 39 minutes to print at this super duper high resolution. It can be really instructive to slice. Once you've sliced it, like I just did, you can go into the preview and kind of ask yourself where all the time went. So it's processing the layers. You see there's 876 layers. The big issue here, do you see where the issue is? It had to generate a crap ton of support up here because of all those curly cues. So what a more intelligent person would have done is probably print it the other way around so that the curly cues are, you don't have as much to support. Okay, well, okay. But you get the idea that there's a whole bunch of support there, okay? So let's go back. Let's forget the support issue for now. What I'm going to do is I'm going to just click off the support, and I'm going to reslice it just so we don't have to look at the support. I think I've railed enough about that topic. And let's take a cross section of this column, and let's see if we can make the world's strongest column. So what we were interested in doing is crushing some columns. So we made a bunch of columns. And then we had a mechanical tester. I think it's in the back room, actually. And we can put up to, I don't know if you remember how much, Kyle, was it like 1,500 pounds or 2,000 pounds? Anyway, it was a lot of pounds. But basically a pneumatic pressing kind of object that could then press down on the thing. And we were not able to crush it. What would typically happen is the model would fail like down here, but then this part would be essentially incompressible. But one of the things that I learned from this exercise that I think is super cool. Okay, watch this. This is super cool. We can step through all the layers, and let's take a closer look at what's going on in the interior features of the column. you can see that it's mostly hollow in there. So as we go through, you can see, let me try to make it, maybe I'll make it a little bit more edge on so you can get a better idea. Okay, there you got a pretty clear view of it. You see that it's mostly hollow here? This is something really, really special about 3D printing, because what we could actually do is, as this thing is printing, I could actually fill that void myself. In fact, I can actually stop the printer at the very, very top if I want. So let's suppose that I get this thing to print all the way out to like just almost to the top part, like right about there. Do you see where the gyroid fill is kicking in? That's really cool. That's coarse gyroid fill. Now you maybe understand gyroid fill really, really well, because as I step through the layers, you see how it goes from one direction to another, to another, to another, to another, and then it gets finer and finer. What I could do is I could stop the print right here. So I can, on the printer, as it's printing right here, I can say stop. And the print will actually stop. And at that point, what I did was I ran over to Einstein's from them, and I filled this column with salt. And then I clicked, OK, continue, and it kept it off. And then I had made a 3D printed object that was filled with salt. And then I was very proud of myself. I thought, OK, how can I make this even cooler? Now I'm going to do the same thing, and I'm going to stop it, and I'm going to fill it with water. And I went and I got a little, like a pipette, and I just filled it with water. And then I said, OK, keep going. Why would I, those physics experts among us, why would I want to fill a column with water or oil? What's special about those things? What's special about filling? Remember, the objective here is to make a very, 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 very strong column. Why the hell use water? It's runny. It doesn't hold the shape, right?
They're incompressible fluids?
Incompressible fluid, yes. The water is like really, really hard to compress. I challenge you to go next time you're in the shower to try to compress some water. You will find it rather difficult. Okay, just about the only way that you can effectively change the density of water is to freeze it. That's it. It's really, really hard to change the density of it. It's incompressible. So you, no matter how hard you pound on it, you're not going to make denser water under normal conditions. And so the really nice thing is you fill your column with water, and now you have extreme compressional strength. So as long as the outermost layer of your column holds up, as long as the bag, so to speak, that holds the water, or the form that holds the water, maintains the shape, then it's, yeah, we just about broke the test rig trying to crush it. We never got anywhere close to crushing the column in that case. So this is an example of something very, very special that you can do with this additive manufacturing technique. Can you imagine trying to do this with anything else? In fact, whenever you, I wouldn't really call it 3D printing, but the way people cheap out and make columns these days, they don't just like, you know, go to Greece or something and haul a 10-ton slab of marble or whatever, and then carve out the thing, right? They don't make columns subtractively anymore, because that was extremely labor intensive and very, very heavy and ridiculously expensive. What they probably do now is make a form, and then they fill it with concrete, and then they cover it with something to make it look like it was made of, you know, a fancier material, right? So fortunately, nobody makes, you know, pure marble columns anymore or anything like that. Not that I know of. They will make, sometimes they'll make the capitals, make them out of marble, and make some of the coatings and stuff like that, but sort of linear. But anyway, let's pause here. And can you think of some objects that can only be made with this additive manufacturing, with 3D printing or any other additive manufacturing technique? Can you think of some, try to brainstorm for a second, think of some objects that can only be made that way? I gave you one example already, which was that curious gyroid fill. Let me grab it. This super weird three-dimensional objects. This thing is a pretty good example of something that cannot be made subtractively. I mean, if you wanted to make this thing subtractively, let me stop. Oh, what was I supposed to click? Stop share. If you wanted to make this thing subtractively, you would have quite a task on your hands, right? I guess you would get a slab of material, and then you would get a very fine chisel, but it's going to be a really bad couple of years to make it, right? Can you imagine trying to make this thing? That would really be rough. So there's one example. Can you think of any other examples of things that would be really hard or maybe even impossible to make subtractively? What about, I mentioned that we have dissolvable support. We could actually 3D print a ball within a ball, and we have a couple of these over at the Rapid Prototyping Lab to show off, I believe. So imagine you got a ball and you got something else that's free floating inside it. And because of the dissolvable support, we're able to make that whole thing in one model, right? If you wanted to make that subtractively, I think what you would have to do is you have to make two hemispheres, and you put your other ball inside there, and then you weld it together, and you try to do a good enough job welding and polishing so that nobody can tell, right? Can you think of any other things that are particularly odd? Things with moving parts, hollow things, plastic block lasagna, says Eric Ma. I don't know what plastic block lasagna is. Is this something you've had? I'm not sure what that means. The blue object he showed us looks like lasagna. It is. It's sort of like a lasagna layer. It is. It's got a whole bunch of layers. So yeah, there's a whole bunch of hollow things and stuff like that. Here's a really weird example that I can give you. It's actually possible. So I have some clients at NRL that are really interested in absorbing energy. So they're interested in absorbing acoustic, absorbing sounds, or they're interested in absorbing, say, a bullet impact, or if a projectile impact that smacks into a wall, and you want to absorb as much energy as you can get. Imagine you can make this kind of meta material. You could actually make this thing. We could powder titanium print this thing. We could make this whole thing out of titanium with plastic in all of the voids. So maybe like some polymer, something flexible, silicone rubber or something. Tell me, what are the properties of that thing going to be in terms of sound or energy absorption? Who the hell knows, right? It's going to be some kind of weird combination of the strength of steel or titanium with the rubbery sort of energy absorbing properties of the rubber, right? So you can make this sort of metamaterials that are like really, really weird. They combine all kinds of weird properties. It could be something that's very, very light, but still very strong. Could be something that is like this and completely absorbs sound of all frequencies. So if you wanted to make the ultimate like sound deadening room or something like that. So you can make a lot of weird stuff. Now let's flip the coin a little bit here. Can you think of some things that can only be made subtractively? So try to think of some things that you would not want to make if you wanted to make something. What is something you would not want to 3D print? Yeah.
I guess like a statue of a person.
Why is that?
I think support would mess up the detail.
Support would mess up. So if we were going to make a statue, you're tall. If I wanted to make a 3D printed statue of you, first of all, it would take forever, right? It would probably take weeks to actually 3D. We'd have to print it in separate parts, and then we would glue you together, like that. And then also, you're right, you have some of us have more overhang than others, but I know, you'd have to have support under the nose and all this kind of stuff, and it would probably mess up the detail. Yeah, you're right. I think that the nicest statues that we've seen, and you can look up some 3D printed statues, they're kind of For the most part, chiseling out seems to be the way to go with a statue, or making a mold and then pouring metal in there and smoothing it out or something like that. Yeah, definitely. Other kinds of objects, I think we already touched on one point here, which is that a tall object, yet I want to 3D print that probably. We do have, David Scheffler is someone he's not with us anymore. He's gone on to work for MITRE, but he's made 3D printed drones, and his drones had very long wings. There's like a flying wing design, and he had to 3D print those things, and they're like 2 or 3 feet high, and that took a long time to 3D print. I mean, to the point that you really just want to print the frame and then just take something else and bend it over. So in real world manufacturing, I think we're usually doing some kind of combination of additive and subtractive, because they each have advantages, right? Has anybody here worked with CNC? Computerized numerical control. CNC, or a mill. Basically what you do is you start off with a block of wood, and then you got a fancy, basically an electric Dremel tool or drill, and it goes and it cuts out your design. So you can make really nice things, like for example, this this wooden scroll that you see here on this violin. This would be a really nice thing to CNC. That would be something you would do. If you had to 3D print this, I think it would take a very long time. Probably wouldn't. And also, okay, the other thing is, let's just talk about materials considerations. We can't 3D print a lot of things. There's still a lot of materials. I feel like every year, every week even, our library of materials that we can 3D print gets better, but we're still not able to 3D print a credible wood. It just doesn't, you know. I actually had some wood filament, and it just kind of looks like wood, and you're supposed to be able to sand it, and didn't really work very well. Okay, so we're fairly limited in the number of materials. At this point, the things that we can 3D print are things that we can melt or spray or make a powder of, and then we hit it with a laser to solidify it or something like that. So there's a whole bunch of materials we can't 3D print with yet, and may never be able to. If you wanted to make a really large structure, then you can adapt you can scale up the 3D printing process. So you could make, I've seen examples of like a 3D printed bridge parts and stuff like that. There's one really spectacular example of how architects are using 3D printing. Actually, let me see if I can open it on this other screen while I'm blabbing here. Start a new window here. Oh no, that's not it. Dubai building. I forget the name of it. There is a really spectacular object being built right here. Oops, sorry. Let me share my screen. I gotta unshare this one. There we go. Get a load of this. This is going to be a really spectacular building. It's going to have, eventually it'll look like this. I don't even know what to think. It's what it is it's going to have, it's going to be mirrored like, kind of like a very cool looking, like some alien ship deposited this thing, but it's covered in this gorgeous calligraphy. And then what happens, the way it'll look at night, I don't know if they have a night view of it, there will be light coming from inside, so then the calligraphy will kind of light up. But every single part of this thing, this is essentially 3D printing. I mean, look at that. It's basically a 3D printing process on a massive scale. They're actually having to go layer by layer and complete this thing. And what they're actually doing is metal 3D printing the outer shell and then putting it onto the framework. So you can kind of get the idea how the 3D printing idea is kind of spreading now to architecture. You can start to get some really, really complex designs. I was looking for an interior view of this because when they do the interior, okay, here's an Autodesk. I think there's an actual tutorial on it. That's not what I was looking at. Anyway, I'll find it. There's a nice little video where the Autodesk people sort of show how they participated in making this design. But when you think about how that's revolutionizing, I mean, contrast this with this over here. Okay, so this over here, there are some older buildings that were probably made with brick and mortar sort of structures. And then maybe some of the larger ones were made with, skyscrapers aren't made with brick and mortar, so you typically have some sort of large frame, and then you adhere stuff to it, and it just kind of looks like it's solid, but actually is very light. And this is a totally new manufacturing technique being used, and it's probably something that you're going to see more and more of in your lifetimes. To us, it's pretty amazing. To you, it will be less so. Okay, so I think we're out of time for today. Mostly, I just wanted to give you an overview of 3D printing, and hopefully, whatever design ideas you have for your ring, hopefully everything you've heard now is going to marinate. And you can kind of think about that over the weekend and think, okay, I can CAD a whole bunch of stuff. Just that I can CAD something doesn't mean it's going to come out very well when I 3D print it, right? I need to start thinking about what are things that I can design that will actually have a reasonable chance of coming out and looking good, right? So maybe start thinking about that, and then we can pick this up next week. I think probably what we're going to wind up doing next week is, hopefully I don't have to talk at all. I would just like to orbit around and help people with their designs, with your sketches and with your 3D printing, the rings and all that kind of stuff. And we'll just hang out and look at designs and stuff like that and chill out and make some cool stuff. Cool? By the way, you're not absolutely compelled to make a ring. If you really badly want to make like a dog tag, or if you want to make a bracelet or something else relatively small, then that's also fine. If you just want to explore some completely different design thing, then feel free to do that. Any questions? All right, if not, then I hope you have a good weekend. I hope your wastewater stays clear and pure. And, and I will see you on Monday.
Really quickly, can I share my sketch?
Uh-huh. Let me give you permission to share.
I think I already have it.
Do you have it already?
Oh wait, no, never mind.
I made you
Like,
co-host, so
yeah.
now you can share. Take care. See you. See you. Ah, this is, what is this? It's a clipper. This is like a nail clipper sort of thing.
Yeah.
Sweet. Looks great. I really like the color.
The one thing I don't really want to get too into is like coloring these hands.
Yeah, no, I don't think you need to. I mean, in fact, I think that having it light like that just sort of shows it. If you could make a design too busy. So like if you shaded that a lot, then you would just be, I think most of the eye would go towards the hands and not the object. So I think what you did there is perfect. One thing that I would be very tempted to do is maybe draw, do I understand correctly that you press down here and that clips here?
Yeah.
Okay, so maybe how about an arrow, just like a curvy arrow that comes here. It just sort of shows that there's motion there. And then you could even, I think you explained this here, but the point is you press here and then this clips here.
Yeah.
Something like that. I mean, like a really, really simple thing. I love the perspective here. So you got a very nice clean view. One thing that I can't quite make out, and you could just put a label here, is where the actual sharp part, I think it's right here, maybe that thing right here.
Yeah, it's like here. It's kind of hard to see. I think I should have had like a more front perspective, I guess.
Well, one thing you can do, if you have time for it, and if you don't mind a little bit of extra work, sometimes what I will do is I'll make an exploded view of something. So what I'll do then is I just draw a dotted circle around here, and then I put dotted lines out here, and in this space do a very, very blown up version of where the blade makes contact with the fingernail. You know what I'm saying? The other thing you could do is just simply drop a label. Just put an arrow here. So like I put like a squiggly arrow like that, pointing to here and say blades. That's fine. That takes care of it. So it just depends on how much time you have. But yeah, I think it looks cool. I like that you have an area that says coarse edge for filing. It looks to me like a couple of arrows, just a couple of strategically placed arrows and labels. would really clarify, because there's that area that's called, do you know what that's called, that area at the top of your, that sort of file area?
I don't know. Yeah, I
It's
think it's
usually
just like
called
a
knurling.
nail file or something.
It's usually called knurling. Let me type it in the thing here. KN knurling. You might look that up. Usually that technique where you take a flat piece of material and you make a whole bunch of indentations that are at cross angles to each other, that creates a non-slip or a filing kind of structure, and that's usually called knurling. Cool.
All right, thank you.
Yeah, I think it looks great as is. Just you know, if you feel like doing
some arrows to clarify
some
things.
arrows, a little bit of text here and there. I think it's gonna be perfect. Awesome.
All right, see you.
Okay, have a good one. See you.